Hello and welcome to this lecture. In this lecture, we're going to start looking at the properties of expected value. Okay, so expected value seemed like a simple definition given the PMF. We'll see it has some very surprisingly powerful properties, and ultimately, when we connect it up with practice, it has really even more surprising properties. So just to motivate a little bit, let me go back and complete this this little casino math that we've been doing. Expected value of gain, etc. So here is a strategy that somebody has come up with. You bet 1 unit of money with probability P1 each on under 7, over 7 and equal to 7. Okay. So with probability P1 you're going to say under 7, with same probability P1 you're going to say over 7, and probability 1 minus 2 P1, whatever the value of P1 could be. It could be 0.3 or something, and then you say equal to 7. And what is the expected gain? Okay. So this is a interesting question here. So this is the probability with respect to the gain. So if you have to find the expected gain here, so with this betting strategy, you will have this probability P1 entering the picture, right? So it's going to be 5 P1 times 5 by 12 times 0 plus P1 times 7 by 12 times minus 1, isn't it? Plus P1 times 5 by 12 times 0 plus P1 times 7 by 12 times minus 1. This is the case where I would have bet under 7. This is the case where I would have bet over 7. And then I do 1 minus 2 P1 times 1 by 6 times 3 plus 1 minus 2 P1 times 5 by 6 times minus 1, isn't it? So it's a straightforward little calculation here. So if you simplify, you're going to get this 0 will not play any role here, minus 2 here, so minus 7 P1 by 6 plus, so this, if you do 1 minus 2 P1 common, I'm going to get 3 by 6 minus 5 by 6, that's minus 2 by 6, anyway it's negative. So minus 1 minus 2 P1 times 2 by 6. Okay. So if you want to add this up, if you can do it, but anyway the news is quite bad. So you're going to get minus 7 P1 minus 2 plus 4 P1 by 6. You can simplify it. You're going to get minus 2 minus 3 P1. No, minus 2 plus 3 P1, sorry, by 6. Okay. So whatever you choose your P1 to be, right, you're going to get a negative expected gain. Okay. So this is negative for all P, right. You could choose P1 to be 1, for instance, you will still get negative. Maybe that's minus 5 by 6 or something. You could choose P1 to be 0, for instance, and always bet equal to 7. You will get minus 1 by 3. So whatever you do, the expected value is negative. Okay, and this is how casinos and other betting companies will play the numbers. Okay, so they'll decide on the gains so that the expected gain goes negative for you. And when it goes negative, in the long run you're going to lose. Okay, you're definitely going to lose in the long run, and this is something that's a useful calculation. So you see but this kind of a property for the expected value, why it represents the average value over a long period, is something we will see later. We will see much later. This is much more practical, much more important. But before that, this way of calculating expected value should be made simpler, and you should understand it better. And so far we've been looking at only one random variable, and typically you will have multiple random variables, isn't it? More than one random variable will enter the picture. In those kind of scenarios, how to handle expectation, and expectation ends up being very useful in those scenarios as well. So our properties will be focused mostly on those kind of things, how to simplify expectations, how to understand expectations from that point of view. We'll start with that, and there'll be some very powerful properties for expectation, ends up being extremely valuable in practice. We'll focus on that primarily, and then later on we'll see some other properties of expected value which give you the sense of what is the long-term average when you observe several instances, and why that is the expected value. Okay, so we'll see that maybe not even this week, maybe in one of the later weeks we'll see that. Okay, so the first thing is let's deal with two different types of random variables. We are familiar with this expression, right? Expected value of x is summation over t in the range, t times probability that x equals t. We'll consider two cases first. Constant random variable. What is a constant random variable? Seems like a bizarre thing, but if you have a random variable x which has this probability property, right? The distribution is probability that x equals c equals 1. That's it. It takes value c with probability 1. Okay. So if that is the case, then the expected value of c is simply c. Okay. So this is a useful identity to remember. Expected value of a constant. Normally you don't think of a constant number as a random variable, right? But you can think of it as a random variable. You take a constant c, think of it as a random variable which takes value c with probability 1 and simply say expected value of c equals c, right? This is something you can do. So this is the first property, very simple property. Okay. The next one is when x is non-negative. Suppose a random variable is non-negative. Okay, it's greater than or equal to 0. You can show expected value of x is also greater than or equal to 0. This is one of those very simple results. You can see here, t, if t is always non-negative, probability is anyway non-negative, right? It's definitely greater than or equal to 0. So the whole summation will be non-negative. Okay, so it's a very simple proof. So these two are easy properties, important enough, but very easy to write down. Okay. This is probably the most central and most important property of the expected value. It's slightly unexpected. A lot of people get surprised by this property the first time they see it, but it's a very powerful property, and it's one of the most crucial reasons why expected value is so popular in analysis of any probabilistic phenomena. Alright, so let me describe what it is. It's a bit of a definition, but the central point is there are n random variables. Let's say there are n random variables now, x1, x2 to xn, and I'm defining a new random variable y as a function of these n random variables. Okay, so this is the most crucial thing to focus on in this whole definition. I mean, the other things are usual, very typical. I'm defining my random variable y not just directly by giving its distribution. I'm saying y is a function of n other random variables. So this can happen in practice. I mean, quite often random variables that we see in a situation, in experiment, it depends so much on other random events and choices that are made, and finally this results. Okay, so thinking of it as a function of n random variables with some joint PMF is very important. Okay, so now once you give me a function like this, I can go and find out its PMF. I can find the PMF of y and the range of y. Okay, ty and fy. Once I know y, ty and fy, I can find its expected value, right? So expected value of y, right? So this is expected value of y, isn't it? If I want the expected value of g of x1, x2, xn, it's the same as expected value of y, and I might compute like this. But what is surprising is you don't need the PMF of y, okay? If you can only use the joint PMF of x1 to x1, and the same expected value becomes summation over all the possible values that x1 to xn can take, g of t1 to tn times the joint PMF. So notice the difference between these two expressions. The first one is in terms of the PMF of y. The next one doesn't use the PMF of y at all. There's no use of the PMF of y. The function is used, and you just sum over all possible values that the random variables x1 to xn can take. The function times the joint PMF of the x1 to xn. Okay, so you don't need to find the distribution of y to find the expected value of y when it is a function of n random variables. This is a very, very important property that this theorem is pointing out. Okay, so you don't need fy. You could find fy and find the distribution. It's not wrong, but you don't need it. The joint PMF is good enough. Okay, so it's a very simple property. On the face of it, it seems really silly and simple, but it has so many powerful results. Okay, it's used again and again and again, this property to derive so many other useful things. I don't want to really prove this property. It's not very hard to prove. Maybe later on we'll see it, but you can intuitively sort of accept this property, right? You have expected value of a function of several random variables. How do you compute it? You simply add up over all the possible values that the random variables take, that function times the joint PMF of all those random variables. So simple enough. In this course, we'll simply take this as the definition. Okay, so and it's trivially to be to this whole thing. Okay, so I don't want to go into the proof here. but it's a very easy and intuitive result to understand. Okay, so instead of proving, I'll just prove by illustration. I'll just show you a few examples and illustrate to you how both these expectations are the same. Here's a simple example. X is a uniform random variable, minus 2, minus 1, 0, 1, 2. Let's look at the function x squared. Okay, so it's 0, 1, 4, and you can see the probabilities you can find. So we've seen this before. A few lectures back, we saw how to find the PMF of a function of random variables. You can use the table method here if you like. Just write it down as a table and calculate. You know that x square will be 0 with probability 1 by 5, will be 1 with probability 2 by 5, and 4 with probability 2 by 5. Okay. Now, if you want to find expected value of g of x, you can do it in two ways. One way is to find the PMF of g of x, which is what I found, and multiply with like this, 0 into 1 by 5 plus 1 into 2 by 5 plus 4 into 2 by 5, you will get 2. You can also do it the other way, right? You simply do g of x, use the g of x, and then use the PMF of x. So this thing came from here, this came from here, and both of them lead to the same answer too. So this is what that theorem was telling you. Instead of finding the PMF of g of x and then finding its expectation using the PMF, you can simply plug in directly from x summation over all values that x takes, okay, and plug in the function g of x, which is minus 2 squared, minus 1 squared, etc. And probability of x taking that value minus 2, you add it up, you will get it, right? So this is probability that x equals minus 2, this is just g of x squared. This is just g of x, right? This is x squared. Okay, so you simply sum over g of x, probability of x. So this guy is what? So this thing is what is this formula again? Summation over t squared times probability that x equals t. Okay, so I have done this here, and this is after finding the distribution of g of x. Hopefully you see how both of them give you the same answer. Like I said, I'm going to simply illustrate this answer, this result, instead of proving it greatly. Okay. So now I'm going to take two random variables. In the previous example, I took only one random variable. Here is two random variables, and notice how I'm writing the distribution. This is just some shorthand distribution. I'm going to take xy takes all these values uniformly. So each of these things have probability, I think 1 by 6, right? Yeah. 1 by 6, 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 1 by 6. So how do you read this? This is basically probability that x equals 0, comma y equals 0 is 1 by 6. Probability that x equals 1, comma y equals 0 is 1 by 6, like that. Okay, that's how we read it. And here is a complicated looking function. G of xy is x squared plus xy plus y squared. You can compute the distribution of it using the table method, right? So how do you write the table method? You can write xy and then g of xy and then the probability of this also. So x is 0, 0, 1, 0, 0, 1, 1, 1, minus 1, 1, 1, minus 1, and then g of xy you can compute. It is 0 here, it's 1 here, 1 here, 3 here, this is also 1, 1. And so from here you can quickly find the probability. This is all 1 by 6, isn't it? Okay. So from here you can find the probability of g of xy being 0, that's just 1 by 6, being 3 it is 4 by 6, being 3 is 1 by 6, being 1 is 4 by 6. Okay, so it's easy enough to find out, and this is the distribution that I'm talking about. Okay, so you can compute once again expected value of g of xy in two different ways. After you find the distribution, you can find it like this. You get 7 by 6. You can go back to the original distribution, right? So here you can see that this is g of 0 comma 0, and this is probability that x equals 0, y equals 0, like that. You just add up everything. So this is g of 1 comma minus 1, and this guy is probability that x equals 1, y equals minus 1. Okay, so you get 7 by 6 here, it's 7 by 6 here, both of them are equal. Okay, so it's just an illustration. I know this is not a proof, but you're not going to prove that result. It's a bit messy with some notation. I don't want to do the proof. Okay, so hopefully you understand this. This is a very, very, very central and important idea in the area of expectations. It's very simple, but you can do the expectation in both ways. If you have a function of n random variables, you don't need to find the distribution of that function. You can simply use the original distribution and add up over all possible values. You will get the same expected value. Okay. So this function property leads to this wonderful thing called linearity of the expected value. Okay, the expectation or the expected value is linear in some sense. What is linear? If you take expected value of c times x, it's the same as looking at expected value of x and then multiplying by c. Okay, the proof is actually quite simple. It's written down here. I don't want to go through it, but this is an important property to know. So if you have a random variable multiplied by a constant, okay, so 2x, 3x, 4x, 100x, whatever, you can take that constant out and simply take expected value only for that random variable. Okay, so that's the first property in the linearity. Okay. Okay. So the next one is much more interesting. For any two random variables x, y, expected value of x plus y is expected value of x plus expected value of y. Okay. So once again, I want to emphasize this property. It's a very simple little property. A lot of people think x and y have to be independent. Only then expected value of x plus y is the expected value of x plus expected value of y. That's not true at all. For any two random variables x and y, expected value of x plus y equals expected value of x plus expected value of y. Okay, whether they are dependent, independent, anything. Okay, so the proof is very simple. If you assume a joint PMF and then you just simply sum it up, you'll see, the function x plus y simply multiplies and the summation distributes over each of those things. Okay, so you need all these summations to exist. We'll assume that. So if you do that, you get this. So this first one is just t1. T1 is what? Just x, right? Expected value of x. This is just t2. T2 is what? Expected value of y. That's it. As simple as that. Okay, you don't need x plus y anymore. You can do x separately, y separately, and add it up. This little property here is extremely useful. One of the most useful properties. In fact, you can combine these two and write like this: expected value of ax plus by is a times expected value of y plus b times expected value of y. Okay, I'm sorry, a times expected value of x plus b times expected value of y. So this is expected value of ax plus by. Okay, so once again, this is very useful. Simplifies so many computations around expected value. Okay, and the proof you can see is very simple. So this linearity property is very crucial. So let's take a few examples. Okay, so let me go back to this example, g of xy being x squared plus xy plus y squared, right? We saw this example before. Expected value of g of xy, we saw 7 by 6. One more way to do this expected value is write this expected value as x squared plus xy plus y squared. Now this is now you use linearity, right? Expected value of the sum of three different random variables the expectation sort of goes inside. You take the expectation inside the summation, you distribute it over summation, you get expected value of x squared plus expected value of xy plus expected value of y squared, and you can find each of these things. They will all add up to give you the same 7 by 6. Okay, so one more way in which the expected value helps you. Okay, so if you look at this very closely, you see that supposing I only have the marginal distributions of x and y. Okay, x is marginal with distribution of x. I know the marginal for y. I don't know the joint PMF. In fact, it's not given to me. Maybe I can't even estimate it. I don't know. It turns out you can still compute expected value of x plus y. Why is that? Because expected value of x plus y is expected value of x plus expected value of y. Okay, so I can find each of the expectations separately, and x plus y is simply the sum of the two expectations. So for any joint PMF, in fact, it's independent of the joint PMF. It doesn't depend on the joint PMF. For any joint PMF, you can find expected values of this form. Okay, so it should involve x alone plus something that involves y alone. You simply distribute the expected value inside, and you need only the marginals. You don't need anything else. Okay, it's nice to know, isn't it? So this is a very powerful property for computing the expected value. So here is a simple little problem where I can use this property. Okay, so you throw a Faraday twice. What is the expected value of the sum of the two numbers seen? Let's say x is the first number, y is the second number. Number on the first die, number on the second die. Expected value of x plus y is simply expected value of x plus expected value of y. We know that the expected value of x is 3.5, this is 3.5, it's 7. I don't need the joint PMF. I don't need to look at the pair of the two numbers, all the 36 possibilities. What is the probability that it becomes 2, 3, 4 till 12? Average it out, nothing. To find the expected value, it's as simple as that. Powerful, isn't it? So that's why the expected value It's a very, very useful thing in practice. So now let's move on to this expected value of the binomial distribution, right? So we saw that this y, when you have a random variable y, which is binomial NP, you have this complicated summation, and I showed you how you can simplify it by cancelling all this, etc. And finally you end up in NP. I'll show you a much simpler method using linearity of expectation. Okay, when you use linearity of expected value. Supposing you have n IID Bernoulli P random variables x1 through xn, okay, and expected value of xi is equal to p, isn't it? It's just Bernoulli P, right? We saw 0 with probability 1 minus p, 1 with probability p, so expected value is just p. Now interestingly, this y, which is x1 plus x2 plus so on till xn, we know from before it's binomial NP. Okay, notice this interesting little connection here. So if you add up n IID Bernoulli P random variables, you get binomial NP. The fact that they are independent is not so important. The fact that they add up is very, very important for me, because now I can use linearity of the expected value. So expected value of y is simply the sum of all these expected values, it's n times p. Notice how easy it became. Suddenly, all of a sudden, there's nothing in this problem while you are struggling with all these factorials and summations and binomial formula and all that. Using linearity of expectation, you get something so simple. Okay, so hopefully you see the power of this simple little property that expected value has. Okay, so the next thing that quite often people with data worry about, they would like the average value to be 0. Okay, for a lot of reasons, it's good to have the average value 0, but in general you may have the distribution somewhere else far away. Okay, so it may be the distribution which is some very large number or something. It may be around something, but you may want to say translate it, move it around, make the average 0. So keep it around 0, but maybe the same distribution as that shifted here. Okay, so is that possible? Can you make average of a random variable 0 without touching its distribution? It turns out it's possible. Okay, so that's by doing something called this translation of the random variable. If you have a random variable x and you add a constant to it, you get a translated version of it. Okay, so what is the translated version? The range simply becomes x plus c, right? So range of x plus c is just range plus c. Okay, every value in the range you add a c to it. And what is the probability? Probability also sort of shifts. Right? Instead of being x equals t, it goes to x plus c being t plus c. So everything is translated. So you have a distribution far away in very large values. You can simply sort of move it close to 0 and look at it with a 0 mean. So this is something very useful. Some people call this centered random variable, or centering of a random variable, or centering of data. Particularly when you have data with mean being very large, you may want to just subtract the mean, bring it down to 0, and many machine learning and other algorithms like that, like to have the mean 0. Okay, so in particular, it's interesting to translate by the expected value. Remember, expected value of x is a constant. You have a random variable x. Expected value of x is just a number. It's not random anymore. Expected value of x is just a number, right? It's one number. Now, what happens if you do translation by expected value of x? Okay, if you look at a random variable y, which is x minus expected value of x, you see that the expected value of y becomes 0. Okay, so this kind of a translation, x minus expected value of x, this is some sort of a centering operation of the data or the random variable. You are measuring any random phenomenon, you might want to subtract its average from it and only look at the variation around it. Maybe it's interesting, right? So otherwise you just get misled by how large it is, while really what is important is the variation. Okay, so this kind of 0 mean random variables, obtaining 0 mean by translation, and what happens to the expected value when you translate, it's very important, right? So in particular, if you look at expected value of x plus c, right, we know what's going to happen to this, right? It's expected value of x plus c, isn't it, right? It's expected value of x plus expected value of c, and that is just c itself. Okay, so this is what happens when you translate a random variable. Okay, so that's nice to see. It's a simple, it's just a fact I'm putting out here because it shows up quite often and nobody really talks about it too much, but this is important to understand as well. Okay, so let me finally close with a simple little problem. We have here 3 bins. Okay, let's call it 1, 2, 3, bin 1, bin 2, bin 3, and some 10 balls are thrown at random, and it could go into any of this with probability 1 by 3. Okay, ball 1, ball 1, ball 2, so on till ball 10. Okay, one after the other we throw 10 balls into any of these bins at random. Okay, and I want to find the expected number of empty bins. I'm interested in empty bins, right? So maybe I'm thinking if I throw 10 balls, maybe number of empty bins will be very small. I mean, it's very, at least one ball should go somewhere. Maybe it looks like it, but still, let's compute the expected value. I mean, if the expected value is small, maybe that's good. Is it easy to compute the expected value? Okay. So here is a little trick here. This is very important. This use of what's called indicator functions. Okay. So I'm going to say x1 equals 1 if bin 1 is empty and it is 0 otherwise. Okay, so this kind of a thing is called an indicator random variable. Okay, so you do this experiment. Okay, you do this experiment, you throw the 10 balls and then you see if bin 1 is empty. If bin 1 is empty, then your random variable x1 becomes 1, otherwise it is 0. Okay, so this is how the bin is defined. Once again, remember what is the experiment? Always think in terms of experiment, sample space, outcome, random variable. My experiment is what? I'm throwing these balls into these bins uniformly at random. After I've thrown 10 balls, I'm going to look at the outcomes. What are the outcomes? Where did each ball end up? And I'm not interested in the location of every ball. That's not what I want. That's a complicated outcome. I want a function of that outcome, which is number of empty bins. In particular, I'm looking at this x1, which is going to indicate to me whether bin 1 became empty or not. Okay. So now the same thing I can now extend to xi, right? This I can say for I equals 1, 2, 3. Okay. So what's the probability that xi equals 1? What's the probability that bin I is empty? All the balls should go into the other two bins. Okay. So that is 2 power 10 possibilities out of the 3 power 10 possibilities. So it's 2 by 3 power 10. Other way to think of it is every ball should not fall here. It's 1 minus 1 by 3 raised to the power 10. All the 10 balls should fall into different ones. So probability that xi equals 1 is easy. Okay. So what's probability that xi equal to 0? I don't really care too much at this point, but anyway, it's 1 minus 2 by 3 power 10. Okay. Okay. So now what is number of empty bins? Number of empty bins is also a random variable. It's actually x1 plus x2 plus x3, isn't it? This is the random variable, which is the number of empty bins. Okay. So finding the distribution here is a little bit difficult. Okay. Finding, so let's say y equals this. Finding fy is a little harder. Okay. Why is that? You can think about why that is so. I will leave it as an exercise for you. Think about how you will find the distribution of y. What's the probability that there's no empty bins, 1 empty bin, 2 empty bins. It cannot be 3 empty bins, isn't it? So all 3 cannot be empty. So notice the difficulty here already. I mean, so these x1, x2, x3 are not independent. They're dependent, and it's complicated to find the fy. But I can find expected value of y. What is expected value of y? It's just expected value of x1 plus expected value of x2 plus expected value of x3, and that is just 3 times 2 by 3 power 10. Okay, and you can see it will be a very small number. Okay, so you can calculate it, be a reasonably small number, so you can be sure that most of the time you're going to expect that all bins are occupied. Okay, so this is a powerful little problem. To me, this problem quite often drives home the point and the power of the linearity of expectation. You should try to find fy to understand what I mean. Okay, finding the distribution here in the balls on bins problem is a little bit hard, but expected number of empty bins is quite straightforward and works out beautifully because of this linearity of expectation and how easy it is to calculate. Okay, that's the end of this lecture on property of expectation. We'll meet again in the next one. Thank you very much.